Hello, everyone. So today we're going to be talking about colligative properties. So a colligative property is going to essentially be any property of a mixture that doesn't actually depend upon the nature of the solute. So it's going to focus more closely on the solvent. So in order to examine a lot of properties of systems, we're really going to want to start by looking at chemical potential. So since colligative properties don't actually depend on what the solute is, it shouldn't be too surprising that they're really going to focus in on the properties of the solvent. So we can look at the chemical potential of the solvent using the expression we developed during Raoult's law for an ideal system, where the chemical potential of my solvent is going to be equal to the chemical potential of my solvent if it was a pure solution, plus essentially a correction for the mole fraction of solvent present. So essentially how concentrated the system is. You may notice, because again, we're generating this as chemical potential, we're essentially treating this section as a size intensive property with no inclusion of the amount of species present, which is going to give us a lot of utility in describing systems no matter their size. Now, one of the other important features of, since we're looking at solvent property, is it actually isn't going to matter whether my solute is volatile or not. So I'm not stuck knowing the extent of volatility or even solubility of my solute, as long as I know its essentially effective concentration. And what this is actually going to, what this equation actually tells us is something very important that we've addressed several times before. That when I'm looking at the chemical potential of my solvent in the mixture, it's always going to be lower than my pure solvent system. And this is essentially going to be due to this natural log of the mole fraction always generating a negative value. And so as a result, we're always going to tend to favor or stabilize a solvent in a mixture over the pure solvent system. And one way of looking at that is going to be through entropy. Because as soon as I add in a solute to the system, it means I've increased the number of ways my solvent can rearrange out around it. Essentially, as soon as you add in one wrinkle into a ordered system, you're going to end up generating a lot more disorder, which again, when we're looking at entropy, is favorable. And since again, we're looking at an ideal system, we're assuming that the intermolecular forces haven't been disrupted that much, which again is one of the things to make note of when we're assuming an ideal solution. But remember that when we're talking about solvent systems, where our mole fraction is relatively close to 1, this actually is a pretty good approximation. So let's go ahead and examine some of these consequences of stabilizing the chemical potential of my solvent in a solution. Well, one of the biggest ones is that if I'm looking at the phase changes of my solvent, when I end up essentially increasing its impurity. So what will end up happening is that as say my solvent would say freeze in order to form a solid, well, this essentially happens when the chemical potentials of my solvent and its solid form essentially become equal. But as soon as I add in an impurity, what happens is I essentially lower the chemical potential, which means I change the point at which that intersection occurs. And because now my liquid is becoming stabilized, that intersection is going to happen at a lower temperature. And this is called freezing point depression because my freezing point decreased. Similarly, because adding in an impurity isn't going to change the chemical potential of my gas phase, I'm also going to see a much later intersection between my now stabilized solvent in my solution with its corresponding vapor. We're also going to see an increase in the boiling point called boiling point elevation. And so this is actually a key feature of essentially these colligative properties. As I increase the impurity of my solvent, I'm going to change the location of my freezing point and my boiling point. So let's go ahead and see if we can kind of figure out how a change in purity is going to move that temperature point. And so in order to do this, we're going to go ahead and focus in on the boiling point elevation. So what we're going to be trying to determine is how the temperature of vaporization is going to more or less change along with composition. And so we're going to do this by looking at chemical potential. So we're going to essentially say that uh, uh, vaporization is going to occur when the chemical potential of my gas, again at standard state conditions, so this includes 1 atm, is going to equal the chemical potential of my liquid. Now, one of the important things is as soon as I add in an impurity, I change the chemical of my liquid, essentially by taking the chemical potential of my pure liquid and adding in this correction term based on the purity or the mole fraction of my solvent. Now, since what I'm really focusing in on is the effects of the mole fraction of my solvent, I'm going to essentially move everything else to the other side and focus in on this natural log of the mole fraction of my solvent. So this, in order to do this, we're going to essentially subtract the mole fraction of my pure liquid from both sides, and then essentially divide by RT. Now, when you do this, you may notice that this top term is essentially the chemical potential of my gas minus my liquid. Well, that's also the exact same definition we have for the changing molar Gibbs free energy of vaporization. So we can essentially replace a term here. Now, one of the important things to note is, again, these chemical potentials regard the pure system, because again, the addition of a solute isn't going to change the chemical potential of my gas, and we're only looking at the chemical potential of the pure liquid here. So again, this is the value that you can go ahead and look up in a reference table or essentially calculate using the means that we've addressed in earlier chapters. So what this essentially does is it lets us relate the temperature with the mole fraction of the species. So what we want to do is essentially look at how temperature is going to change along with mole fraction. So in order to do this, we're going to need to take a derivative. And specifically, we're going to take a derivative of our composition with respect to temperature, which again is going to be analogous to taking the derivative on both sides. Well, we get a relatively simple derivative here on our left, because that's what we're looking at, is how these two changes are correlated. Now, over on the right, we can go ahead and pull out all our constant terms, which in this case is just our gas constant. What this leaves behind is the change in the free energy of vaporization over T with respect to T. Now, let's be honest, this guy looks a little bit frightening until we realize we've already solved this problem. We solved this problem when we were looking at how total entropy changes with respect to temperature. Yep, this is our good Gibbs-Helmholtz equation. So we can essentially substitute in the answer we achieved from looking at this back in chapter 3. So when we do this, what we end up finding is that the change of our composition with respect to temperature is going to be related to the negative of the vaporization enthalpy, so essentially talking about how much energy goes into the bonds, over RT squared. Now, in order to try and essentially relate the mole fraction with respect to temperature, we're going to essentially move all of our temperature terms back over to the right. So now we're going to be looking strictly at the change in composition with respect to the change in temperature. And this will let us focus a little bit more on how boiling point, or when the system's at equilibrium, is going to essentially relate to this mole fraction issue. So in order to do that, we're going to need to integrate both sides. So we're going to go ahead and integrate starting at our pure conditions and going to essentially whatever mole fraction or composition we're trying to examine. So when we do this on the right, we actually get a little bit lucky, because when we have the natural log of mole fraction of the pure species, well, that's the natural log of a mole fraction of 1. So a natural log of 0, natural log of 1, which is 0. So the difference in between our two natural logs becomes really easy. On the left here, all we're left with is the natural log of the composition of my solvent. Over on the right, what we can do is essentially pull out all of our constants, which is the enthalpy of vaporization and R. And here we're going to assume that the enthalpy of vaporization isn't going to change too much. And this is actually a fairly good approximation because in most cases, the temperature change of our boiling point is going to be fairly minor. Then what we have to do is just like on the last side, we integrated from the pure composition to our solvent composition. In this case, we're going to integrate from the boiling point of our pure species, so this is our normal boiling point, to the boiling point of now our new mixture. And again, all that's left on the inside is dt over t squared. Well, this is a good old, this is a familiar integral, and we're left with essentially negative t, which eliminates the negative sign here. Sorry about that. Over enthalpy of vaporization over R, 1 over T minus, again, our starting conditions. So when we go ahead and do that, what we can do is then try and simplify the left side of this equation. So when we do that, what we end up with is the natural log of the mole fraction of our solvent, which again is a little problematic because we're trying to describe our solute. So we'd much rather describe the system with respect to how much solute's present in the system rather than solvent. So we can do this with a simple substitution of 1 minus the mole fraction of solute. Now, one of the important things to make note of is that if I have a system that has more than one solute present, the solute I'm going to actually be talking here is the mole fraction of all solutes present. So if I have a more complicated system, we're going to essentially not be giving the mole fraction of any individual component, but the mole fraction of all the solutes put together. Now, we can even simplify this left side a little bit more by looking at what happens when you take the natural log of 1 minus a relatively small value. Because remember, we already made use of the fact that this system is behaving ideally, which is generally going to only happen when we're near the solvent condition. So A is behaving as a solute, which means that B is going to be exclusively a solute, or at very low concentrations. So as long as we're looking at it being a solute, let's use a fun trick of logs, which is the natural log of 1 minus x, essentially just gives us a value of x. And so we can then rearrange the right side by taking a look of, by switching, by getting rid of the negative sign by moving the 1 over the new boiling point minus 1 over our pure solvent boiling point minus 1 over our new boiling point conditions. All right, so now we have a little bit kind of cleaner of a set of equations, but let's be honest, we really hate working with the differences of inverse variables. So what we can do is make use of a trick we've kind of seen before, which is I'm going to multiply this left-hand term by essentially t over t, or 1, and the right one by t prime over t prime. What this does is it guarantees that both terms have the same denominator. So now what I can do is just combine the top terms. So now I get t minus t prime over t times t prime. Now let's actually take a moment to think about what these terms mean. So t minus t prime is essentially my new boiling point minus my old boiling point, or the pure boiling point. So this is essentially just the change in my boiling point. And on this bottom term, we're generally going to assume that since I'm not adding too much x, that both of these boiling points are going to be fairly close to each other. So in that case, what I can do is, since I already know the boiling point of my pure system, I can go ahead and say that these two are close enough. I can treat this term as my boiling point of my pure solvent squared, and then the top term just becomes the difference in boiling points. So this is often slightly rearranged and expressed as a boiling point elevation equation. And this can be summarized as the difference in my uh, original boiling point. So essentially, the increase of my boiling point can be related to the mole fraction of my species through essentially this constant called Kb. So this is my boiling point elevation constant. And as we've seen previously, that's going to be related to our ideal gas constant times the boiling point of my pure system squared over the enthalpy of vaporization. So this is actually quite a useful feature. So one of the common uses of essentially boiling point elevation is the fact that I can introduce a solute of unknown identity. And as long as I know the enthalpy of vaporization, and again, I want to emphasize it's the enthalpy of vaporization of the solvent, then I can determine, and I measure the change in the boiling point of my solvent, I can essentially figure out what the change in mole fraction was. And this can actually be a very useful way to try and determine the molecular weight of an unknown species. And again, I also want to really emphasize that with my boiling point constant, all it depends upon is the ideal gas constant, the boiling point of my solvent, and the vaporization and enthalpy of vaporization of, again, my solvent. All of these properties are just solvent dependent. So again, this is a quite useful way to just look at the mole fraction of the solute in terms of things that can be measured from the solvent alone. So again, its boiling point, at its new boiling point, its old or pure boiling point, and its enthalpy of vaporization. It's also worth noting that you can do a very similar procedure using the freezing point, because again, as the boiling point goes up, the freezing point is essentially going to decrease. And it's also going to be related to, again, the freezing point of the pure substance and the enthalpy of fusion. So again, with several simple variables, we have a very elegant way to essentially describe changes of our system. And one of the things that's worth noting is that while these my freezing point and boiling point constants can be determined based on first principle properties, in practice, they're often going to be replaced with experimental parameters that essentially can kind of capture some of the difficulties due to non-ideality of the system. However, it's worth noting that boiling point elevation and freezing point depression aren't the only colligative properties we can deal with. So next time, we're going to deal with two other colligative properties, most notably solubility and osmotic pressure. Till then, take care.